Not every differential equation is separable, at least on the outset. Some equations that don't initially look separable, in fact, can be rearranged with a clever substitution to become separable. One type is called, of those are called homogeneous differential equations. Before we define a homogeneous differential equation, we should define a homogeneous function. We say that a function f of x comma y is homogeneous of degree n if it can be written in the following form. If it can be written as f of tx comma ty, so we're going to, whatever the function's rule is, we're going to replace x and y with t times x and t times y. And if you can rearrange this, or importantly factor out the t's that result as t to some n, where n is what we eventually will say is the degree of this function, times the original rule of the function, xy. This is very similar to the test to see if a function is even or odd. However, this time we're going to try to factor out this new constant, and then whatever degree that, whatever exponent this constant or this value of t ends up having in the end, we'll say is the degree of this homogeneous equation. So as an example, the test for if this is homogeneous, here's a function of x and y, 3x squared plus 4xy minus y squared. To test if this is homogeneous, and I'm going to show that it is homogeneous, and I'm also going to find its degree. I'm going to figure out what f of tx comma ty is, which in this case is 3tx squared plus 4tx ty minus ty squared, which is 3t squared x squared plus 4t times t is t squared, x times y is xy, minus t squared y squared. Or factoring out, looks like every term has a t squared in it. T squared and then 3x squared plus 4xy minus y squared. And this is, note that this is in fact the original function. So therefore, f of tx comma ty is in fact t squared times f of x minus y. This means that this is in fact homogeneous, and the degree is whatever this exponent is, which is in fact 2. So this is homogeneous of degree 2. We say a differential equation in totality is homogeneous if it can be written in the following way. We say that the differential equation dy dx, if it can be written as a function of x and y divided by a different function of x and y, a differential equation of this form is homogeneous. This is homogeneous if f and g are each homogeneous and of this degree and of the same degree. For differential equations of this type, there's a common or better known as a standard substitution that'll be effective for solving these sorts of differential equations. In that substitution is we're going to substitute out y, and we're going to put this expression v times x in its place, where v is a function of x. We're not concerned of exactly what this function is, but it's implicitly a function of x. And along the way, what we're going to end up doing is substituting this expression in. This will turn our differential equation that didn't used to be separable into one that is separable. We'll separate, solve. We'll get an expression involving v's and x's. And then in the end, we'll back substitute and replace v with what v is equal to, namely, by rearranging this, it'll be v will equal to y divided by x. And in the end, we'll end up getting a solution that will have only y's and x's in it. Further note, this is going to be useful as well. Further note that with this substitution, we're going to need to figure out what the differential operator is, what dy dx, what dv dx is in this case. Because of this substitution, this also always ends up being true. Using implicit differentiation, if I differentiate each of these two sides with respect to x, on the left side I get our friend dy dx. Since y is a function of x, we're going to use an implicit differentiation and the product rule to come up with an expression for this. Using the product rule, I should get the following. I should get v times 1 plus dv dx times x. And these two substitutions are going to come in useful for solving and turning a homogeneous differential equation into a separable one. So here's an example of that. We're going to solve this differential equation, find a general solution, and then we'll also find the particular solution for this combination, for this initial condition where y is 3/2 and x is 3. So this differential equation is not separable. There's no good way to get the x's and y's on one side because of the structure of the numerator here. I can't factor out an x or a y from each side. There's just no good way to do this as is. However, you can check that this is in fact homogeneous. That if you replace x and y with t times x and t times y, the top is homogeneous of degree 1. The bottom is homogeneous of degree 1. Each are homogeneous. Each are the same degree. Therefore, this common substitution or the standard substitution is going to help us. So we're going to use the substitution of y equals v times x. So how does that work? Everywhere I see, I'm going to replace y with v times x, and I'm going to replace the dy dx also with this being the derivative of this implicitly, which we saw just a second ago, is v plus dv dx times x. So what do we get? Replace the dy dx with that expression. We get v plus x times dv dx. That is equal to x plus, instead of y, 2 times v times x, all divided by x. Note that in the numerator, I can factor out an x, because each term now has an x, and this leaves me with a 1 plus 2v, and divide by x. And what do you know? Now I can cancel these two x's that are here. So I now have this expression to deal with, v plus x dv dx. This is equal to 1 plus 2v. This is now separable. I can get the v's on one side. X dv dx is equal to 1 plus v. And I can get the v's on the left and the x's on the right, in the same way we were solving the separable differential equations just a second ago. I will divide by 1 plus v. I'll divide by 1 plus x, 1 over x, excuse me, and then I will multiply both sides by dx, the operator dx, to separate this out. And I will get the following. 1 over 1 plus v dv is equal to 1 over x dx. Again, we'll eliminate these operators by integrating. This gives me the natural log of 1 plus v on the left side. This gives me the natural log of x plus c on the right side, the constant of integration. And again, a standard trick, let's undo this natural log by making all of this as an exponent of e. So let's see, we get some inverse operation happening here. This is 1 plus v on the left side. This is e to the c times e to the natural log of x, which is a times e to the natural log of x. Or better yet, a times x. I'm going to get v by itself. We'll subtract 1. So v is equal to ax minus 1. Remember, v from before, note that y equals v times x, or v equals y over x. So I don't want this v. I want initially I want using in terms of my original variables, but we're almost home free. Y over x equals ax minus 1. Multiply both sides by x, and we have the general solution as differential equation. Y is equal to ax squared minus x. We get this particular solution for the coordinates y equals 3 halves and x equals 3 by, again, substituting in those values. So at the point, so for the solution that passes through the point 3 comma 3 halves, we have the following. We have 3 halves is equal to a times 3 squared minus 3. Add 3 to both sides, or 6 halves plus 3 halves is 9 halves, is equal to 9a. 3 squared is 9, so a equals 1 half. Therefore, the particular solution, in this case, y is equal to 1 half of x squared minus x.